Welcome back, everyone. Hope you had a good weekend. So we'll start in the new week. We're right in the middle of the semester. So I remind you that we're having the forum on Thursday. And then its logistics will be the same as in as for the quizzes, except you have twice the time, right? And of course, so I will be set up an exam via Gradescope, and then I'll send you the notes, send you the directions. So you'll be given 2.5 hours to complete the test. Yeah, so like there's extra time for uploading solutions. Of course, you can use this extra time to solve them as well. Will it cover 14.7 and 14.8? 14.7, let me remind myself what it is. Maximum minimum values, no. So like that's the, yeah, so that would be too soon, right? So we'll talk about 14.7 and 14.8 today, tomorrow. And then we'll have a discussion on those matters on Friday. Yeah. Right, so we have this minimum, maximum, Lagrange multipliers. Yeah, so those are important topics we have to, we don't have to rush with them. Yeah, that's right. Yeah. Yeah, any other questions? Is anything from this week going to be on midterm? No. So right now we'll start at 14.7 minimum and maximum values. And according to our tradition, the material which is taught on the given week is not tested on that week. So no. Yeah, so this material will be included into next quiz, which will be next week. Right. So and then I think today and tomorrow we'll talk about minimum and maximum values and Lagrange multipliers. And on Wednesday we'll do a review for the midterm. Okay. Yeah. So let's discuss it. If other questions will appear, I can answer them. I apologize. So let's recall how we deal with the story for the function of one variable, right? So in one variable calculus, so we have let's draw some graph of functions. So it has a well, we would say that this is a local maximum. And this is a local minimum. And how do we define those terms? Well, we'll look at the neighborhood of those points. So that's the point x1, and then we take a small neighborhood, say x1 plus a, x1 minus a, and then we compare values of the function in every point in this neighborhood against this one. And then if f of x1 exceeds, so is greater or equal than f of x for every x which belongs to this neighborhood, then we say that x1 is the local maximum, right? And similarly, if the inequality goes in opposite direction, go at x2. So you have, that's x2. Then we'll take some neighborhood here, x2 minus b, x2 plus b. And the same thing happens for x between, which lives between these points. Then we say that point x2 is a local minimum, right? So the adjectives local refers to the fact that this inequalities needs to be satisfied only within those neighborhoods, right? And then as opposed to global minima or maxima, where the those inequalities must be satisfied in the entire domain of definition of the function, right? So for example, if you take f of x, which is equal to x squared, as we know that x equals 0 is the global minimum. To understand how to what's going on, so in order to study global behavior of the function, not only you need to understand what's going on in the neighborhood, but you can also examine what happens everywhere else in the domain of definition. So often, if you have a boundary, so the function is bounded from like the domain is given by some interval, right? And then it happens that the value of the function at the boundary of that interval exceeds or is the smallest out of everything, and that will be your global maximum or minimum, and it has nothing to do with any derivative analysis in the vicinity of those points. Okay, and then can somebody remind us what was the condition for the local maximum? So if function f was differentiable, right? So what was the condition for the local maximum, and what was the condition for the local minimum? So function has local maximum if what? So excuse me. So yeah. So that's right. So the if a function has a local maximum or local minimum, right? So what was the condition on the derivative of the function? Right. So here we had the derivative of the function x1 was equal to 0, right? So well, gradient, we'll get to gradient later, but it just functions one variable, so it's normal derivative. So it's f prime of x1, x2 is equal to 0. Notice that there might be some peculiar situations like this, right? So we have a function. So it is important though to claim this, like the arrow the arrow goes. Well, yeah. So you're already right. You're already talking about the sign, right? So, but first, yes. So first, we need to. So Hannah is saying what happens about the change of the derivatives, right? So or the second derivative, right? So or concavity of the function. So, but first, we need to establish that partial derivative is 0. Excuse me, partial will come next. Derivative is 0, right? And that includes this various peculiar examples like this one. So you have a function that does something like this, like it goes. And then it flattens, it plateaus. Well, that meant to be a flat thing, but anyhow, and then it goes up. So according to the definition, right? So every point, like over here, there are infinitely many, will be a well, you can twist it either way you want, right? So it can be either a local maximum or local minimum, right? Because if you pick, say, if you take this point over here, right? And you pick neighborhood like that, then it will be a local, yes, this point is a local maximum, but say point from the middle, say this one here, if you take neighborhood like this, right? So then it will be a local minimum, but if you take a neighborhood like that, then it will be a local maximum, right? So like it always happens in calculus, if you push your imagination to extreme, you can get to some weird examples. Okay, yeah, and since Hannah mentioned that, so we can define maximum or minimum if we decide what happens with the second derivative, right? So Hannah is saying local maximum derivative changes from positive to negative, right? So that indeed the tangent here was sort of the tangent vector was making positive angle, then it's making negative angle. So therefore, what shall we say about the second derivative? Right, so therefore, different colors. So the second derivative of x1 should be what? Okay, so second derivative is the space of change of the first derivative, right? So and here second derivative of x2, yes, it should be greater or equal than 0, right? And here it's less or equal than 0. Okay. So today let's discuss what happens if how this generalizes to functions of many variables. Well, as you can imagine, there's more ways to go, because the function can increase in x and decrease in y, right? And it can have various peculiar behaviors in all directions. Yeah. So first, let's give a definition, which is rather so it's essentially it's the same definition, only that two variables are involved. So say function f of xy has a local, so let me try to write it at the same time. So has a local maximum or minimum at point AB if for all x inside, well, let me say it in words. I know most of you don't like the symbols. So if for all x and y from a small open disk centered at AB, so the following thing is true. So so f of xy is less or equal than f of AB, and respectively f of xy is greater or equal than f of AB. So this condition about small disk, it means that I don't like this color. Okay, let me pick something different. Okay, you can make a different one. Let's see this one. Right, so this condition implies that the so for every x such that distance from square root of yes, x minus a squared plus y minus b squared less or equal some delta, right? Some positive delta, which is arbitrary. As long as delta is positive, it works, right? So if such positive delta exists, then it will do, right? And yeah. So and then in first instance, this is called a local maximum, and here is called local minimum. Okay, I'm not going to attempt to draw a plot here, so let me just we'll switch to Mathematica after a while. But first, let's prove a statement about that. Right, so theorem says that if f has a local maximum or minimum, then it's both first order partial derivatives must vanish. And of course, you should probably know, so maximum or minimum, we can refer to them as extrema. Right, so we have a local extremum if the function is either has a local maximum or local minimum. So if f has a local extremum at x, y equals, so yeah, of course, yeah, so as before, we're taking the function of two variables for simplicity, right? Everything that I say easily generalizes to functions with more variables. We'll look at some examples later. So yes, at this point, and well, we need to ask them that they exist. And its first order partial derivatives exists. So fx and fy exist at that point. Because it may not be the case very well, right? As we know, then they have to vanish, right? So f prime of x at ab is equal to f prime of y at ab. Is equal to 0. Yeah, forgot the most important part. So both have to vanish at the same time. Now, the analogous statement in calculus of a single variable is known as Fermat theorem, right? So it's not the famous Fermat theorem about existence of solutions of polynomial equations, but yeah, it's a Fermat theorem from calculus. No, theorem that Fermat proved when he was a kid. I'm kidding. So we can, as we know, we can sort of, the idea behind this partial derivative is that you can reduce function of two variables to function of one variable. So if you say let g of x be equal to f of x b, right? So we are fixing, we're saying that y is a constant and looking at the change of x. So if f of x comma b has a local extremum at ab, then so does g, right? Because these inequalities here, they have to be satisfied, well, in any direction, right? So for every value, every point in that small disk, this should be true. So then therefore, g of x has a local extremum right? So it has a local extremum at x equals a, right? And now we can use Fermat theorem. From the calculus. So the single variable says that g prime of x of a should be equal to 0. But of course, g prime of a, by definition, is the partial derivative of x at b, right? By construction. So therefore this is equal to 0. And analogously, you can put a function h of y, assign it f of a comma y, and then it would follow from Fermat theorem that the derivative at x equals y equals b is equal to 0, which implies that the partial derivative of y at ab is equal to 0. Okay. Now, so it's only here, it's a statement in one direction. Then the opposite statement is not true. So in other words, if you have a function of two variables and then at some point two partial derivatives vanish, then it does not always the case. It doesn't always mean that the function has a local extremum. Can you give me an example? We already had some surfaces previously, right? When we talked about quadratic surfaces, we had some examples when you have a function which looks like both derivatives would vanish at the point, but it's not an extremum. Well, actually, so Sarah is saying if you take a function y equals x cubed for one variable and then the derivative is 0, but there is no local minimum or maximum. So let's get back to my comment in the beginning. So actually there is, right? So because we define local minimum or local maximum, as you see here, there's a. Oh yeah, I'm sorry. Yeah, that's right. Yeah. So yeah, good. Right. So another example, yeah. So we take example, yeah. So y is equal to x cubed, right? Its derivative at x equals to 0 is equal to 0, but of course it's not. Yeah. So here there is no neighborhood, right? So this is not the minimum or maximum. Yes. Yeah. Okay. So that's example from analysis of one variable. So how about two variables or more variables? Can you think of an example where this would do? Also, one naive idea would be, of course, to take what Sarah is saying, take this parabola, cubic graph, and then just foliate it, right? So like you would still have a function, f of x y, which is equal to just x cubed, right? So it does not depend on y, right? So this way, this will be like a valley. This will be the line of constant. This will be the y-axis, and then of course the derivative in this direction is 0 because it's flat, and derivative of this direction, of the opposite direction, is also 0 because it's x cubed. And clearly it's not a local minimum and maximum because you slide. It's like a slide, right? So you don't do. But is there any other example that we already know? So that will be just a classical example. So we need to find a function that would sort of has a maximum. So which function has maximum in one direction and minimum in the other direction? Yeah, a saddle shape. That's right. So another example would be to say that z is equal to x squared minus y squared. And so the it would look like you would have kind of growing parabola in one direction, right, and then kind of the well, yeah, not a great picture. Yeah. So, but yeah, we'll switch to mathematical. Yeah. So like basically here the yeah, I should do them in opposite in different directions. Let me try one more time. I thought I knew how to draw saddles. Yeah, so the would do something like this, right? The yeah, so you have this set it goes like that, and then here it would do like that, right? And then it would go up, and then here it will, and then there it will go down. And so here, obviously, if you take this function, take derivatives, they both 0 at point 0, 0. But if you go in y direction, you would fall off. If you go in x direction, you would climb up. Right? So this is so-called. So here, and this for this function x comma y equals 0, 0 is the saddle point. So it's a technical term. It's not only, well, I mean, it's used many places, right? So for example, often you can have a function. So you have a function of many variables x1 through xn, which in the neighborhood of some point behaves. If you do the Taylor expansion till the quadratic part, then you have well, possibly with some coefficients, but then you can have some of the functions can go with pluses, some of them can go with minuses, right? And then that's also called a saddle because it would grow in one direction and would sort of decrease in the other. Yeah, so opposite is not true. Something this phenomenon does not happen in function of one variable simply because there is no room for that. Okay. Good. So now, how we decide then, right? So, what's the analytic tool of understanding what's going on with the behavior of the function at the near the critical point, near the extremum, right? So then well, so with the in calculus of one variable, we looked at the second derivative and looked at its sign, right? So therefore, that would determine the concavity of the graph. So here, obviously, we need to look at something that knows about change of the function in two directions, in x and y. So here's the theorem. I'm not going to bore you with full proof, but we'll look at some examples. So it's the second derivative test, which is applied to functions of two variables. So we suppose that all second partial derivatives are continuous on a small disk centered at the point AB. So they exist in continuous. Okay. And then suppose that the partial derivatives fx of AB is equal to 0, and fy of AB is equal to 0, the first partial derivatives. So therefore, fab is the extremum. Okay, and now define D to be the determinant of the following matrix. It's fxx, fxy, fyx, fyy. Right, so because the function is continuous, then we know that fyx and fyy, this xy and yx partial derivatives are equal to each other, right? And so that's equal to fxx times fyy minus fxy squared. And now here's the statement. So if, and this theorem is specific for two functions, right? So for more functions, you have to be, there'll be more terms, more conditions. So if d is greater than 0 and fxx of AB is greater than 0, right? So then fab has a local maximum. FAB is a local maximum. So this point, yes. So, right. We'll comment this in a moment. But basically, this determinant. So if you look on the diagonal terms of this matrix, then so you can. So this is a symmetric matrix which you can diagonalize by changing the basis, right? And then essentially it will boil down to a statement that both diagonal elements are positive, right? If you do it this way, and then if D is positive and fxx of AB is less than 0. Oh, guys, I'm so sorry. Minimum, yes, minimum. It's like, minimum. Yeah, so if both are positive, it looks like a minimum, right? So for example, you'll have a paraboloid. That's a question from Sarah. If the second derivative is positive, then yeah, that's right. So right, yeah. So it's a minimum, right? And then if D is greater than 0 and f of x is less than 0, then what does it mean, right? Again, if we're using the same consideration, if you reduce this quadratic form to be diagonal, so the only way to have, basically there are two ways to make a determinant positive. Either both diagonal components are positive, so that's case 1, case A, or that both diagonal components are negative, right? So that's case B. So here, therefore, the f of AB is a local maximum. Okay. And then so if you go to functions more variables, then we have more conditions, right? There are more ways to make a plus sign, right, of the determinant. And finally, if D is negative, then it's neither maximum nor minimum. It's not a maximum nor minimum. Okay. Why did you do the matrix in the theorem? This is somehow related to the cross product. Not really. So it's related to the second differential. So okay, so let me comment on the proof. So see, well, when we talk about function of one variable, we have this. So there's one way to write the Taylor formula like this, right? So that the change of the function is equal to So delta f is a finite change, right? And then you write a Taylor formula like this. You say it's f prime. So say yes, delta x is equal to x minus x0, and you're doing a Taylor expansion of the function around x equals x0. So therefore, well, Taylor formula looks like this, right? So 1/2 factorial f prime prime of x0 delta x squared plus higher terms, right? Now, if you see it at a local extremum, this is 0, right? And you have to look at this term. So delta x is positive, so therefore the behavior of the function completely determined by the sign of the second derivative. That's the essence of that theorem. Now, in functions of two variables, I don't remember. I was supposed to do Taylor formula in this class, but I'm just going to sort of give the intuitive understanding how that would do. So now you have basically delta. There's delta x and delta y, right? So delta x is x minus x0. Delta y is equal to y minus y0, and then similarly you can look at dx. It's the differential, right? So we don't usually write a formula, Taylor formula like this, but that's kind of it's in this form. It's easier to generalize to higher dimensions. Okay, so do you agree? Is that what you expect to be? Okay. Now what we're going to do, we're going to generalize the differential to differential of the function of high dimension. So now delta f of xy, it will be what? It will be f prime of x of x0 y0 dx plus f prime of y x0 y0 dy. So these two guys will disappear if you're sitting at a critical point. But then you'll have this quadratic form, right? 1/2 factorial, and it looks like basically you can write it as a matrix. Dx as a dx dy, it's a row multiplied by that matrix that we had: fxx, fxy, fyx, fyy times dx dy. Why is this the case? Well, it's a certain calculation that that we can do. If we have time on the discussion, we can. I can do it for you. But sort of intuitively, so you should think of this as a this second differential, right? So it's the it's the analog of this term over here. Right now we're coming back to this linear algebra thing, right? So when can we have so now we need to analyze the behavior of this form, and that's why the determinant is important, right? So it's the so if this determinant is so we can say something definitive if the determinant, if this matrix has a positive determinant. So Sarah, does it give some intuition behind what's going on? Yeah. And then yes, so and then of course, like, so basically that's how the Taylor formula or Taylor series works for everything. So then we have, so you cannot write it as matrices anymore, but it can be written in terms of tensors, right? So then you would have, so say triple derivative over a, b, c. Let me write it like this, and then we have dx. I don't expect it to be familiar with tensor notation, but anyhow, so you'll see what's going on. So dx db dx c, where a, b, and c go from 1 to 2. So this is basically and then so you need to look at all possible derivative in all directions, right? And then you convert it, you convolute it with a with a cubic expression now, right? And then basically it's it goes in all directions. So for example, you'll have a term here like f triple prime xxx dx cube and so on. Right? There'll be eight terms, right? 2 cubed terms, plus and so on. So yeah, Taylor formula for the multivariable calculus is well, pretty much the only way to represent it is in terms of how the finite difference of a function is expressed as a linear combination of well, as a series in differentials. Okay. Other questions? Right. Okay, now let's look at some pretty pictures. There you go. So here, let's start with this one. So remember what I told you that the well, so what will you describe? What do you say about this function here? So the x squared plus y squared. What happens at x equals to 0? Does it have a maximum, minimum, or anything? So the limit doesn't exist, remember, right? So therefore, the function is not continuous, so we should not. But nevertheless, right? So if you would approach the so you would know that the so yeah. So which way can you describe the local minima and maxima? What's going on around x equals y equals 0? So how would you tell where are the maxima, where are the minima? Function is not differentiable, right? But that just, you know, it's an unfortunate circumstance, but still you can say something, right? So can you say definitively, say if you have a maximum on, so remember we had 2 lines here. On this line, function was taking constant value 1. On that line, function was taking constant value -1. So which points are local maxima, which points are local minima? So Han is saying approach from x equals y equals maxima, approach from y equals -x, local minimum. Yes, and then you have to exclude the origin, right? So basically, right, so every point here, you can take a small disk, and then so here clearly to the local minimum, and you can take any small disk around any point on the green line, and that will give you a local maximum. So you can make, so every point on the green line except the origin is a local maximum. Every point on the red line except the origin is the local minimum. That's right. So here, because the function is not differentiable, you have to, well, you have to do something different. Okay, now let's plot the saddle. to see it works a little bit more. It doesn't change if it does. Yeah, so the if you go, this is 0, 0. If you go in this direction, you have local maximum, right? If you go in that direction, you get well, it's not, it shouldn't say local maximum, right? So the partial derivative in x direction is positive, is partial second derivative in x direction is, yeah. So let's calculate the determinant here, right? So fxx is equal to 2, fyy is equal to -2, and then fxy is equal to fyx is equal to 0. So therefore, this determinant delta is equal to -4. It's less than 0, and therefore the point x equal to 0 is neither minimum nor maximum. Of course, if you switch the sign, right, so everything will be all right, right? So you have perfect local minimum at x equals 0, y equals 0. Okay. Good. Any questions? Let's do one more example. Some more interesting quadratic polynomial, or maybe even cubic polynomial. So let's say take 10xy minus 5x squared minus 4 minus x to the 4 minus 2y to the 4. See, do we need to go somehow? So this example would be interesting. Yeah, never mind. Let's do it. So like there's a. I'm just trying to see if there's a minimum. It's gonna hard to see what's going on here on the flat, right? So therefore, let's see let's try to investigate it using calculus. So here's the function, right? So I'm going to take its derivative. Okay, so since we're in mathematical, I'll just do it over here. And so derivative of that over x is this, and then so remember that the same as with the function of one variable, conditions for so loci where the first derivatives vanish, they'll only be candidates, right? Candidates for local minima and maxima, and then we need to sort of check if they actually those points, right? So now let's solve this equation. So when they equal to 0 at the same time, so there are a bunch of solutions here, right? So the first one is, well, this x equals to 0 solution from here, right? So this x equals to 0, y equals minus 3/2, and then x equals to 0, y is equal to 0, right? And then there are 6 more solutions, right, which you can get by basically these are solutions of some cubic equations, which we cannot. I mean, there's a formula, right? There's a root formula, but it's you can spell it out, right? It says it's a root of some cubic polynomial here, evaluated at that point. So the yeah, so right. So these are the solutions. So now we need to examine all those points for what's going on with the with this second with the determinant of that matrix, right? So say we do, let's calculate xx and then xy, and then we calculate x should be the same, and then yy. And then we take the matrix, or we just fill in with those values. And then its determinant will give us, there's some polynomial with round numbers. So let's evaluate this sum at those solutions, right? So then the if x goes to 0, first let's do x equals to 0, y equals to minus 3/2. So that's positive, right? So and then so the determinant is positive, and then let's calculate. You didn't highlight the negative for the fourth matrix? Sorry, I don't understand. Oh, thank you. Yeah, thank you. Yes, thank you. Yes, you have to be careful. Yes, that's even. Yes, a slightly simple. Yeah, thank you. That will be important. Right? So it says 720, so it's positive, and then well, we need to evaluate each of them here. So the function, the second derivative itself is negative, right? So here, therefore, what's probably happening is that the this point 0, minus 3/2 is a local maximum, right? Because the determinant is positive, and so this is negative, and this is negative, right? So let's see where 0 minus 3/2 are. Try to make it bigger. Okay, maybe do. Yeah, so I think it's the where is that point? Minus, yeah, I think it's somewhere here, right? So if you do it, if you go to white a little bit longer, so minus 3 to 1. Yeah, that's right. So you can see here, it looks like, yeah, and now it's getting somewhere. So it looks like a slope of this kind of, it's the surface of, say, jet engine on the plane, for example, right? And then it kind of falls down. But here you see, like, if you take this line, it looks like it's flat here. But nevertheless, sort of the derivative vanishes at this point, and it does look like it's a local maximum. Right. So let's see what how the plot looks like if we cut this graph along x equals, if you plug in x equals to 0 and see what happens in the y direction. And so well, I think it probably didn't do it. It doesn't actually look like it. Sort of it kind of raises a little bit. So if you do -3 to 2, yeah. See here. Now it's clear what goes on. So it's sort of goes. So if you plot this function, it behaves like that, right? So here, see something interesting going on. So this point is indeed a local maximum, but because if you look at some, oh no, it's not the one. I'm sorry. Yeah, that's not. So here it's -3/2, right? So here this is -3/2, right? And this is a local maximum. I just rotated the plot like this. So let's do it. Yeah, it's kind of hard to distinguish for the three-dimensional shapes, but nevertheless, do longer. Yeah. Okay. Yeah. So there's a local maximum here, and now let's see what happens at this point, which is 0, 0. Right. So let's evaluate. Yeah, so 0, 0. What's going on with the determinant? The determinant is 0, right? So therefore, according to our theorem, it's inconclusive, right? So if the determinant is so here is 0 and here it's negative, and yeah, so basically if you look at so 0, 0 is this point over here, so we can draw. Now let's put y is equal to 0, and we plot that. So here is a maximum, right? But over here, it's neither, right? So if you kind of zoom in on this one, it does look like the cubic thing. See, so it's neither maximum nor minimum. Yeah. So notice that when this matrix is degenerate, right? So when the determinant is 0, the test is also inconclusive, right? And therefore, we know that. So this point is a local maximum, and this point is neither. It's neither maximum nor minimum. Okay, and now any questions? Okay, now what are these guys, right? So it's the why do they? Well, and these guys, they're imaginary, right? So see, this has imaginary roots, and so one solution is imaginary, so we should not consider this. But we need to treat the other one. So let's try to solve it numerically, right? So this line we can forget because it's imaginary solution. But then there are this couple of points plus and minus 0.838 for x, and then y is 0.64. Let's see what they are. So I think there are probably those slopes where the kind of starts falling off from those, right? So the sorry. Down here. Yeah, I think these are some points, right? I think right, so if you look at this from above, so this image that will go to maybe from, yeah, so that the x value, and then so what were they? So x is equal to plus minus 0.8 and y is plus minus 0.65. Right, so so and y is equal to plus, right? So these are two points somewhere here, right? And then it does look like they're derivative derivation, but sort of the well, yeah. So let's try to evaluate the determinant of those points, right? So see what's going on. So the x-axis here is negative, and the determinant here is also negative, right? So which means that nothing is going on, right? So like it's neither minimum nor maximum, right? So if it happened just because again there's a little saddle point approximation there, which is let's try to plot it. Let's, for example, evaluate x at this point. And you can plot it. It looks like this. So there's a little maximum here, and now we need to do the y thing. To plot it like that. To see it's we should go from, of course, here there's a maximum, and then in y we go 0.64, so it's somewhere here, and x is equal. So it's a maximum in both. Let's see why is it not working. So if you do the plus, it still stays the same. Interesting. Yes, we have this wedge at this point, and then the. Well, I mean, what may happen is that sort of it kind of behaves differently in different directions, right? So the I'll just check if I did the right calculation. So if you take, yeah, so here the derivative determinant is negative, right? Okay, and then let me check that one. integral determinant is positive, and the second derivative is negative, right? So the other point, the other point is the maximum, right? So these two, these two will be maxima, right? And of course, it's because it's symmetric, the same should happen for the other one. So it's negative here, right? And then it's positive here. So these two are local maxima, right? We talked about these, right? So this is a maximum, this is nothing. This is a complex saddle, we don't talk about it. And just, and then this x and y are apparently, again, so it's, they neither maximum nor minimum. Although from the graph, it's not quite clear what's going on because it does look like it, let me check once again. So take x and y here. So take derivative, evaluate that. It's negative. Yeah. Anyhow, so apparently something the maximum. It doesn't look like maximum. So it's neither maximum nor minimum. Okay. So you can see it might be a bit complicated, right? So because the so sometimes it's even hard to draw it to see what's going on using using the computer. But the test works. Okay. Any questions? Let's see if I want to change plot range to make it sort of look more pronounced, right? So from minus, yeah, so we need to do the from the -2 to -3 to 0. Ah, there we go. And now we're getting somewhere. -3 to 1. Ah, I see. Yeah. So right. Okay, and then we draw. There we go. There we go. Yeah. And now we're getting somewhere. Yeah. So I apologize for going slow on this, right? So what does it look? Does it look like what to you? What comes to mind when you see this shape here? I would say it looks like a T cell from the immune system. Fish tail. Well, okay. Yeah, there we go. So now let's examine that again. So the slingshot. Yeah. Nice. Yeah, imagination, go for it. So here, right? So these are two maxima. So yeah, now we can everything is fine. So what we had, so that guy was a local maximum. It has coordinate, I believe, what was that? 0, 0 minus 3/2. It's a maximum. Okay, now this point 0, 0 was nothing, right? So it was not, well, it's, yeah, neither minimum nor maximum. And then these were two maxima, right? It's something like, well, we had those calculations here, and then there are two saddle points, right? So we're just gonna not so easy to isolate. So remember, I drew for you. So we drew the cross section, right? In X plane in the Y plane of those two saddles, and a bit deceivingly, the function was look like a dome like that, right? So it was it looked like it had a maximum on both plots, but again, it doesn't mean that the function actually has a maximum. Just it has a saddle only. Sort of to see the saddle, you need to look at a different direction. So these 2 points were. I'm going to scroll down for a bit, and then I'll return back. So the negative 0.84 and the plus minus 8.4, and then 0.64. Anyhow, right? So as well as say we paint in red, we paint local maximum. So there are 3 local maxima and 2 saddle points. Saddles, and these are maxima. There we go. Yeah, now it looks much better. So in those maxima, the determinant was negative, positive. Excuse me. Determinant was positive, and the fxx was negative. And in the saddles, the determinant was here it was 0. Right? So no, I'm sorry, no, it was negative. Right? So was it? I forgot. Sorry, what was it? What was that? No, it was negative. It was negative. You need to line back on the. There we go. Yes, the determinant was negative. And the sign of the fxx did not matter. Yeah, there we go. Yeah, if you want to think, I can include this kind of problem in one of the tests so you can use the computer. What does it mean for the extreme when the determinant becomes 0? Then it also means that it's inconclusive. Yeah, so the test doesn't tell you anything useful, right? Like so here in the so it was 0 at this point, right? At 0, 0, it was 0, and then so you need to investigate further. It's like convergence tests for series, right? So if you have ratio test, and then if the ratio is equal to 1 in the limit, it doesn't mean anything. You have to look further. Sure. Okay. So yeah, so I think it might be a good idea to just let you play with the computer and then do this kind of problem. Maybe for the quiz next time. Maybe there won't be time limit. Like I can add this problem without any time limit. Okay. Good. Yeah, so I'll send you the mathematical code so you can play with it. Okay, let's get back to so those were local minima or maxima, and now let's talk about absolute minima or maxima. So as I mentioned in the beginning, absolute maxima means that absolute extrema refers to the phenomenon when these inequalities they are satisfied in the entire domain, right? So so, but before I go, let me show you the theorem, which is analogous to the theorem in calculus of one variable. So it's about a function that is continuous on a compact set, right? So compact is sort of closed and bounded set. That's how you can define it in topology of Rn. So, and if you have a function, in this case of many variables, which is continuous on a compact set, then it attains its minimum and maximum. And we can formulate it for functions of many variables. So let f1 f of x1 through n be continuous on K, which is a compact. This is a K is a subset of D, where D is a domain, and K is a compact subset. Then F attains its minimum and maximum on K. And so that should be familiar from a similar statement should be familiar from the calculus of single variable. The proof of this theorem is quite similar, right? So, and yeah, so it's equivalent to what is called open mapping theorem, or again, so let's not prove it here. Instead, let's focus on the corollaries. Compact subset, yes, subset. So then I remind you that compact means closed and bounded. Okay, so let's remind ourselves what closed means. So it's like the span of the input variables. Not sure, somehow you use some linear algebra terminology here. So when you say that there's a closed set, what is it for the, it's a subset of Rn or some, let's say R, right? So in one dimension. What is a closed, how we define a closed set? It has something to do with the limits, right? So closed set is a set that contains all its limiting points, right? And bounded means that you can put it in a box essentially. Right? So closed means it's contains all limiting points. And so, for example, the reason why interval 0, 1 is closed is because if you take a sequence, any sequence inside the interval, the limit of that sequence will be contained in that interval, right? So sequence 1 over n, it approaches 0, and 0 is inside the interval. So if you exclude 0, you take an open interval, it's not closed because of that reason. Yeah, and also bounded. Now, in higher dimensions, well, boundness simply means that you can put it, confine it in some box, right? So let's say there's some shape in 3 dimensions, and then you can embed it inside a parallelepiped like this. so that so there exists, or maybe a cube, there exists some number b bigger than 0, such that absolute value of this vector x is less or equal than b for every x inside the set S. And then absolute value means that you have this inequality in all directions, right? In x, y, z, and as many directions that you have. Right. So and then so clearly this compactness here is important, right? Because it's very easy to find counterexamples, right? So find the counterexample, not the counterexample, but if you relax the condition for the compactness, it's very easy to find the function that does not attain its minimum or maximum on k. Right? So in one dimension, if you take this interval to be from 0 to 1, which is not compact, and then for the function, you take 1 over x. Right? So it does not attain its maximum at all. It does attain its minimum, of course, right? So here there's no maximum. Actually, it does not attain minimum either, right? So no maximum nor minimum. But then, yeah, so if you take function sine x on 0, 1, including, then of course it attains both maximum and minimum. So therefore, in order to find global maxima, right? So global meaning that we have, it should be so global definition. If we have global maximum or global minimum, if at AB, which belongs to the domain of the function. So yeah, so the so yes, we have a global maximum minimum at a point D if f of x y is less or equal f of AB, and correspondingly f of xy is greater or equal then f of AB for all x, y from the domain. So therefore, the algorithm of finding minimum and maximum would be this. So first, find local extrema. And so you would calculate, derivatives, put them to 0, and then check the quadratic form. Sort of find its sign, whether it's bigger or less than 0, and then make your conclusion about local maxima and minima. And second, you need to check the boundary. Right? It may happen that the function actually takes bigger value on the boundary than, or smaller value on the boundary than anywhere on the set. So these two, of course, assume that the function is differentiable and continuous. If it's neither, then you have to just look at what we did with the function xy over x squared plus y squared. So you need to try to evaluate it at some find its value and compare it with the value of the neighboring points. So let's give an example when the second part of the check the boundary is important. Let's plot another graph here. right? So we have squared minus 2xy to y over 0 and 3, y between 0 and 2. See here, you can ask ourselves, where is the minimum, where is the maximum? So already from the plot, it's clear that this tip over here is the global maximum, right? Because it has it has the biggest value. Okay, but sort of let's go over the let's sort of let's go over the algorithm, right? So first, let's find its critical points. So its x derivative is this thing. Its y derivative is that. Kind of easy to solve, but nevertheless, since we're doing everything on the computer. So there's only one, there's a 0.11 here. Oh yeah, 1 is over there, right? So 1 is here. So that's the global max. That's probably global maximum, right? So, and it's if you do the plot range a little bit, if you zoom in a little bit, yeah, you can see here from 0. See that this looks like a saddle here, right? So let's check that this is a saddle. Now we'll calculate the other derivatives. So we do xx, get 2. We just need to calculate 3 of them, right? So xy and yy. So the matrix would look like 2, 0, minus 2, minus 2. Right, its determinant is equal to -4, right? So it's always negative. Therefore, there's no chance that we're going to get a local maximum, right? So there's no, and as you can see here, there's a saddle, right? So yeah, it's not surprising. So there are no local maxima in the open rectangle. So if x is between 0 and 3 and y is between 0 and 2, and there are no local minima or local maxima. However, well, we just need to investigate what goes on in the boundary. Right? So clearly, if you just see what's going on, so the point 3, 2, right? So if you evaluate this at 3, 2, it's equal to 1. It doesn't look like 1, does it? It looks more like a 9. I'm not sure what's wrong. Yes, it would be 9 minus 8. Because it's 3, 0. Yeah, thank you. Yeah, so yeah, there you go. Thank you. That's right. Because it's 3, 0. Yeah, so it's this corner. So here it takes them the maximum value, and then the minimum value it's a 0, 0 when it's equal to 0. So therefore, maximum, so global maximum at 3, 0, right, and global minimum at 0, 0. Yeah. Okay. Yeah, so that's the global thing. Mm-hmm. Good. Now we have a little bit of time left. I think we should not probably start the new topic, which is Lagrange multipliers. But I think we have just enough time to prove the theorem about the sign of the determinant and how the sign of D determines if you have the maximum or minimum. Unless there are any other questions. So remember, we have this claim that if D, which is the determinant of fxx, fxy, fyx, fyy is positive, and then fxx is positive, then we have a local minimum. Good. So, so as I said, it's to prove it, it's a certain maximization problem, a certain optimization problem in linear algebra. So let's recall the directional derivative, right? So the du, the directional derivative with respect to unit vector u, right? So say we have a vector u which has components h and k, right? Such that h squared plus k squared is equal to 0 or is equal to 1. So we have our point, x0, y0, and then we're picking a direction u, and asking ourselves what happens, how the function changes as we move around in these directions, right? So the directional derivative looks like this. So it's the scalar product of the gradient vector and the vector u. And now let's calculate the second derivative. So we apply the derivative twice, right? So d2u of f, which is du of the thing before, so it's fx times h minus times k. So now we need to take the gradient of this vector and dot it with hk. Yes, plus, thank you. Right. Good. So we'll take the derivative. So therefore, it will be d over dx of that thing fyk times h. and then plus d over dy of this thing. Times k. Right, so that gives us fxx h dot h, which is 1, right, plus fxy h dot k. And then you probably already see how this 2 by 2 matrix in the differential sort of is framing itself. And then plus fyx h dot k, and then plus fyy k dot k. So then, as we discussed, I'm sorry, it's not dot. It's these are the components, right? So this is just h squared. I should probably write it h squared, and then this is k squared. K squared. So that equals to fxx h squared plus 2 fxy hk plus fyy k squared. Right, and now let's complete the square, right? So because in order to get the sign definiteness, we need to complete the square, and in terms of linear algebra, that will correspond to a certain diagonalization of this form, of this two form. Right. So let's take out f of xx, and then have h squared plus 2 fxy divided by fxx times hk. So here we add fxy over fxx squared times k squared, right? And then we subtract fxy squared divided by fxx, because one of them canceled, times k squared. And finally, we write the last term, so plus fyy times k squared. So now we can make, can bring them together. So it's fxx h plus fxy over fxx k, everything squared, and then plus k squared over fxx, and here also we bring it together under the we're grouping these terms together, fyy squared. Okay, so that's what we get after the after calculation of this thing. So I remind you that's the second derivative, it's d2u f. Given by this formula. Okay, so now in our condition, we say that we know that fxx of this point AB is positive, right? So therefore, this whole first term is strictly positive, and we also know that and this is D, right? So this is D, so this is positive. And therefore this is positive. So therefore everything is positive, right? So therefore, no matter which direction you go, right, along every vector u, you always have second derivative is always positive. Therefore, sort of every slice of the graph, every section would give you a curve which will be concave down like this, right? And that would show that this is the global, this is the local minimum. Right. So for every vector in a sort of wherever we go in every direction, you'll get a local minimum. Now, to prove part B, you need to group the terms a bit differently, right? So you need to show that well, then you'll need to single out the fxx, but in slightly different way, in slightly different order. So like the so then basically, if it's negative, then well, you need to, I believe, yeah. So the computation for part B will be slightly different, but anyhow, similarly, you can show that if the derivative is negative and the discriminant and the determinant is positive, then you should have a local maximum. Right, so that's the kind of calculation for two variables, and for high variables, for high number of variables, you should look at some this big matrix and then multiply it by the row of differentials from the left and by the column of differentials from the right. Any questions? So we have several minutes left. We can do maybe an example or two. Yeah. Do we have any questions about the midterm? Anything about the previous problems, previous topics? What are the chapters covered at the midterm? So a midterm will cover the chapters. We talked about the first 4 weeks, right? So that's where is it? Yes. So yeah, so we'll have weeks 1 through 4. So it's all up to 14.7. So not including 14.7. So for it, yeah. So then so today, so tomorrow we'll do 14.8, and then yeah, and then on and solve some problems. Will there be a practice midterm? Yeah, I should be able to send you some practice problems. Yeah, so we have a big database of practice problems. Okay. Is Wednesday going to be a review session? Yes, on Wednesday we'll do the review session. So tomorrow we finish chapter 4. Wednesday we're doing the review session. And there will be additional office hours at 2 when you're welcome to come and ask more questions. Okay. Can you please record the discussion session? Absolutely, yeah, I record everything. So I think I record every meeting except maybe if it's some office hour where only one student comes and they ask some question which may not be interested to everybody. Yeah, so everything has been recorded. And I think I should organize our videos a little bit better. So probably I just put them on my website. I should put links to each of the video with a short description of what this video is about. So this way it will be easier for you to review. Otherwise, we have like order of what 50, no, not 50, maybe 20, 25 videos or so. Do you have any additional tips for the review? So I will just go over the homework. So yeah, so first, yeah, so I will just go over quizzes or their solutions, and you analyze your mistakes if you had made any on the previous quizzes, and look over the homework. So just a review solutions of quizzes and homework will be the best strategy, and perhaps solve some problems, additional problems if you had trouble with them before. So you can just open the book and then look at like pick a problem and solve it. And you can bring, if you do not know how to do it, you can bring it to the discussion on Wednesday or office hours. So I think it will be maybe like order of 10 questions for 2.5 hours. It should be okay. Okay. Great, thanks for joining in. I hope it was fun today with all these pictures. Yes, so I'll see you guys tomorrow then. Right? Thanks, bye.